All right, so I kind of stumbled into this with one of the classes earlier today, and I thought it would be beneficial for everybody to just kind of review. Look kind of at a 30,000-foot view of what we're trying to accomplish here with our two different methods. So we've talked about we have the short method, we have the long method for these calculations, right? Short and long. When we are doing, we'll talk about our long first. When we're doing our long calculations, we're going to take one of our reactants, doesn't matter which one it is, we're just going to pick. We're going to figure out how much of the desired product we can make. Then we're going to take the other reactant, and we're going to figure out how much of that same product, whichever one we pick, we can make using our second reactant. Then, to figure out which one is the limiting, we're going to compare amounts of products to each other. And remember, the least you can make is the most you can make. Okay, so we're comparing products when we're doing the long method. Now, it could be grams of product, it could be moles of product, it could be liters of product. The units don't matter. What matters is that we're figuring out how much product we can make, and then we're comparing based on that. Okay. Now, the short method is where we take one of our reactants and we convert and figure out how much of the other reactant we would need to use up all of that one. We're not worried about products at all, we're just comparing reactant to reactant. And then we're going to compare how much we need, or how much is consumed, which is the answer that we get at the end, to what we're given. And that will tell us our limiting reactant. Okay, so this short method is great for finding the limiting reactant and our excess reactant. But it doesn't tell us anything about the amounts of products that are produced, right? Our long method helps us ID our limiting reactant and how much product we can make. But it doesn't say anything about the excess reactant. So we really need to be able to do both of these and figure out contextually where we're going to start. So when we look at this first problem from last night's homework, we didn't do this one in class yesterday, did we? Okay. So let's look at how we would attack this one. So it says some rocket engines use a mixture of hydrazine and hydrogen peroxide as propellant. The reaction is given by the following equation, which is the limiting reaction or limiting reactant in this reaction when we get these two values of hydrazine and hydrogen peroxide. Okay. And then it asks how much of the excess reactant in moles remains unchanged, how much of each product in moles is formed. Are we going to have to use both the long and the short method? Yeah, we are. Because we got to know how much product is made of each of those products. We have to figure out how much of our excess reactant is there. And we have to ID our limiting reactant. Now, in some cases, not all cases, but in some cases, we can evaluate the information given to us and determine our limiting reactant before we do any math. Can we do that with this one? Are you sure? I can. And I know you guys can too. You got to think about it though. Which reactant is used quicker? How do you know that? Okay, so it's used twice as fast as the hydrazine, right? Which reactant do we have more of? Wait, so the hydrogen peroxide is, we have less of it, and we use it twice as fast? Which one do we run out of first? The hydrogen peroxide. Do we have to do any math to figure that out? So sometimes we can figure it out without doing any math. In this case, we can't. We can just look at the problem. We can say, hey, we have less of this, and we use it twice as fast. So hydrogen peroxide is going to be my limiting reactant. Okay. I know that from the get-go before I do any math, right? So in this case, I've already answered question A. It always is helpful to just sit down and think about this stuff before you start just writing numbers down. Make a plan. Evaluate. What do you know? What can you figure out? Save yourself as much work as possible. We just figured it out without doing anything. Okay. Now, looking at the next one. How much of the excess reactant in moles remains unchanged? Is this a long one or a short one?
Short.
And we're going to do the short one, right? Okay, so we're going to go reactant to reactant. In all of these other questions, once we've identified our limiting reactant, that's the one that we're going to start with. Okay, so what we would do here is we would say, we're going to start with our half mole of hydrogen peroxide. And this one's actually like a super simple problem because it's already in moles for us. And now we're just going to use our mole ratio. And we're going to relate reactant to reactant. So in this case, our mole ratio is 2 moles of hydrogen peroxide for every 1 mole of hydrazine. Okay. So how much, well, here, we'll just do the math real quick. So we end up using or consuming, that's the other way that we see this, 1/4 of a mole of hydrazine. So you can see it termed as used or consumed or you needed that much hydrazine to react all of our hydrogen peroxide. Now to determine our excess, we're just going to do a little math. Well, what did we get to start with? We started with 3/4 of a mole. So this could be our have or our given. This is our starting amount. We used up this much. So that means that we have a 1/2 mole in excess / leftover. That would be hydrazine. Hydrogen peroxide is our limiting reactant, so hydrazine is our leftovers. That's our excess.
So what's the reason we just don't subtract it? Is it because it's not always consistent? Because if you subtract...
Are you saying like subtract what?
Yeah, the limiting reactant, because we found that out in A, but we didn't do the math for it. So if you do end up doing the math, we need to subtract it.
If you do so you have to do the short method to figure out how much excess reactant you use up.
Yeah, so if you do end up doing the short method.
And for A, yeah, then you would just subtract. Yeah. We just skipped all the math for A, which I'm not sure is a good thing in the long run, but I want to show you that you can save yourself some work if you think about stuff. Okay. So then question C, and you're all about saving work, right, Connor?
No.
Okay, good. All right, so how much of each product in moles is formed? So now we're just going to do a limiting reactant calculation to figure out how much of each of our products is formed, both nitrogen and water. So we're going to take our 1/2 mole of hydrogen peroxide and convert that into moles of nitrogen and into moles of water. In the case of nitrogen, we've got a 2-to-1 ratio. So we're going to end up with 1/4 of a mole of nitrogen. And in the case of water, we have a 2-to-4 ratio. So 1/2 times 4 is 2, divided by 2 is 1. So those are the molar amounts of the products that we can end up making. All right, before we do anything else, turn to your neighbor, tell one aha, and one question you still have.
Skipping
Yeah. So I said I wasn't sure it was a good thing that I did that. All right. Anybody want to share an aha? Marcus, what was your aha?
You don't necessarily have to do the math to find the answer.
Exactly. It's all about being efficient, right? It's about efficiency. Okay. Any other ahas?
Well, the whole thing was an aha. Like, I still didn't understand it after yesterday, so going through it again was a lot.
Okay. All right. Now, who still had a question, or whose neighbor saw the question? Aubrey.
This all like, just barely makes sense, but like, my, I
Just disagree with you never had.
it's not really a question.
So that's a more practice thing. We need more practice so we can be more confident. What else? Any other questions? Are you guys too afraid to ask? Marcus?
I have a quick question. So if I, when balancing the equation, accidentally went double and forgot to like reduce it, so like instead of 1 to 4 to 2, or 1 to 4 to 1 to 8, or 1 to 2 to 1 to 4, like it is up there, I accidentally did 2, 4, 2, 8, would that be counted against me, or would that, it's still technically balanced and everything, all the math checks out?
Yeah, the math would check out. Like, I'm not gonna punish you for that
Okay.
in this unit because we're not necessarily super concerned about balancing equations. You have to do it to be able to get to the right answer. You actually did eventually. Yes,
So
sir.
I feel like it's pretty hard to memorize both of the equations, just like and to know what these both equations, you know?
Okay.
That's my thing.
So here's what I would say. Don't try and memorize a method because each problem's unique. There are some similarities and there's some consistency. What we want to do is be a critical thinker and a problem solver. Like, what do I have? What do I need to find? How can I get from where I'm at to where I want to go? And I think one of the things that will help that is practice will help us become more comfortable in those unique situations, right? I will say this, like, on that sheet that I just handed you, 1 and 2 and 3 and 4 are exactly the same problem. I just changed the units and the reaction. That's it. So we're gonna do number 1 and 2, and then you guys will get to practice on 3 and 4 and 5 and 6 before we actually I think 5 and 6 are the same. Roughly the same idea, yeah. So let's look at 1 and 2 on there. I want you to see, look at number 1 on the additional practice problems and see if you can figure out the limiting reactant before we do any math. Just think through it in your head.
We have to balance it.
Probably. I mean, it would help.
Maybe just a little.
Maybe just a little. Has anybody figured out which one's limited? Michael, which one do you think it is?
The liberty is nitrogen.
Thumbs up if you agree with Michael, thumbs down if you disagree. Bunch of haters!
What's going on there?
Why is nitrogen the limiting? Even though there's more of it, why isn't it the limiting?
Because there is more of it, but nitrogen is a lot less mass, therefore it uses a lot, less, and you need a lot more. It's the weight.
You know, you're just having trouble
Yeah.
communicating a little bit. Okay. What's the molar mass of nitrogen gas?
1.01.
Nitrogen 28. Okay, so how many moles of nitrogen roughly do we have?
Oh.
Because we have 28 grams divided by 28. So we have 1, right? How many moles of hydrogen gas do we have? Like 13-ish, right? 25 divided by 2 is like 12 and a half. 13. Like that. It says we have 25 grams of hydrogen. The molar mass of hydrogen gas is 2, because hydrogen is 1, there's 2 hydrogens, so it's 2.02. 25 divided by 2.02 is 13. So we have 1 mole of nitrogen gas, we have 13 of hydrogen, even though we're gonna use hydrogen gas 3 times faster than nitrogen. We only got 1 mole. It's gonna disappear quick, right? So, can you see how we can think through logically and arrive at the right answer without having to do any math? Yeah, and I'll be honest with you guys, a lot of times, the reactant with the smaller mass is not the limiting. And that's done on purpose, because everybody's like, oh, that's the one that we have the least of, gotta be the limiting. So just kind of tuck that one away. Chemistry teachers can be kind of tricky sometimes. They're lazy. I mean, I'm not tricky. I like to show that stuff to you guys so that you're aware. But sometimes they're mean. Is that?
You show us some things to.
No, I at least tell you it's coming, right? Okay. All right. So in this instance, for number 1, we've identified our limiting reactant. Okay. Now, let's just say that we hadn't done that for the sake of argument. Let's say we hadn't done it. Now, let's use the log method to do this problem, because it's asking about how many grams of product can be produced, right? So when we talk about how many grams of product, that's like a long form. That's best for long form, right? Based on this diagram right here. If we're talking about product, probably the long form is the best. Okay, so we'll do a long form just to prove what we did. Okay, so we're gonna start with 28 grams of nitrogen. Let's say 28 grams of N2. Our first step is to convert it into moles. We always got to get to moles. Then we're going to put our mole ratio in there. That equation isn't balanced, but you guys have already balanced yours already, so you know it's a 1-to-2 ratio between nitrogen, and in this case we've only got 1 product, so we don't have to worry about it. Our 1 product is ammonia. And then the last thing we'll do, because it asks for a mass of ammonia, we're going to convert from moles to mass. Now we could convert from moles to volume, right? We know how to do that. Actually, questions 3 and 4 ask us about volume rather than mass. So we can do this 17.03 grams of ammonia. Okay. You're gonna plug and chug real fast, and somebody help me with the math here.
Yeah, about 28.
What's that?
Yeah, about 28.
About 28?
Yeah.
I don't think that's 28's not right. It should be closer to 34. So you have 28 divided by a little over 28, multiplied by 2, then multiplied by 17. So actually, I think it's closer to 39 and 40.
Oh,
Yeah, you're 34 minus 6.
Yeah.
34. Okay. So we'll call it 34 because we only have 2 sig figs in our first measurement there. Okay. So if we use up all of our nitrogen, we can make 34 grams of ammonia. Yes, sir.
Where the atomic, or the mass for ammonia would be 17.04?
Oh, 17.04, yeah. Sure. It's not going to change our final answer. Yeah. No, Michael's checking. Hey, he's checking on me. He's keeping me sharp. It's okay. Okay. Now we'll run the same thing since we're doing the long form. We'll run the same thing for hydrogen. We have 1 mole, H2, 2.02 grams. Marcus, he's a man of precision. It's a 3-to-2 ratio this time. And then we'll put in our molar mass again at the end there. Okay. Somebody help me out with the math, I can't remember this one. Yeah. Somebody doing that? Gavin, you got math?
like 142.
142? So we're round it to 140, just for sig fig's sake. Okay, now, what's the least we can make? 34 grams. And the least we can make is the most we can make. Okay, so this is the limiting reactant. I'd go through and label these on my paper right away if I was you, just so I wouldn't forget about that stuff. So I got my limiting reactant, my excess reactant labeled up, and we figured out how much product we can make, how many grams of ammonia we can make. So we're all done with number 1 now, right? So we go down to number 2, and it says how much of the excess reagent in problem 1 is left over. So now this is the short one because we're talking about reactant to reactant. So we're going to do one calculation. We're going to start with our limiting because that's the one that we start all this stuff with once we've identified it. We said our limiting was nitrogen, 28 grams. We have a 1-to-3 ratio. I do remember this one. This makes 6.1 grams of hydrogen gas when we round it to 2 sig figs. So this is my consumed. That's how much is used up by my reaction. To find my excess, I've got to take my given sad trombone. Subtract what gets consumed in the reaction, and that gives me my excess, which is 18.9. That then becomes my excess there. Right? Okay, turn to your neighbor and tell them what was easier about this one than the last one. Yeah, that sounds about the same. Okay, what was easier about this one? Okay. Did it get any easier?
I think it's just getting easier for practice.
All right, I want to take, let's see, work period, about 20 minutes. Yep, okay. I'm going to give you guys the rest of the period to work on our homework. Now, here's the thing I'm going to say. So, we have 20 minutes to do the rest of this front side. So the additional practice is, the back of each of these is a different type of problem. It's percent yield. We haven't come to that one yet. I don't want to add that to today at this point, okay? So don't do the back yet, okay? Of either one. The back of both of them are percent yield. They're all percent yields. So I want you to work on the front of those, okay? So let's work on the front. You guys can work with a partner. You can work by yourself. You're a loner. But let's make sure we respect personal space and also are productive.